In the last week of classes today, we will close down on the estimation in the sense of discussion on estimation methods, and then very quickly we will discuss how to apply these methods to estimating signal properties and time series models. Now, before I begin, I know we kind of rushed through the nonlinear least squares, but as I said, there is not much to analyze there so easily. So, it was more of learning what is the difference between linear least squares and nonlinear least squares. And as I said, the difference is that you move from the notion of regressors to gradients of the predictors. Otherwise, the remaining results more or less follow. Now, having said that, I have really condensed a lot of extensive work on the nonlinear least squares literature, and normally you will see in some preliminary texts or preliminary material on nonlinear regression on this idea of transforming variables, explanatory variables, if you know the type of nonlinearity up front. So, going back to the ideal gas law, suppose I want to predict the temperature using pressure and volume. If I know through the physics or the chemistry of the process that at least for an ideal gas temperature varies proportional to the product of pressure and volume, then I can construct a regressor up front. Or sometimes if I am estimating, let us say, some Arrhenius constant from the rate of reaction, then in other words, if there is an exponential relation between the predictor and the explanatory variable, I take the logarithm and so on. So, these are the class of transformation methods where you transform a nonlinear regression problem to a linear regression problem. In doing so, it is all right when you are doing it at high school and so on, because basically the idea had to be given to you that you could transform a nonlinear regression problem to a linear regression problem. But it is now time to know that in doing so, you could be transforming the errors in the data as well. Okay, suppose y is the measured variable and x or u is the independent variable, and y and u share an exponential relation, then I could take the logarithm of y and then rewrite everything in terms as a linear relation between the transformed y and the explanatory variable. But remember, since we said y is a measured variable, the errors in y also are transformed. So, question is now whether you assume Gaussianity of the errors in the measurement or Gaussianity of the errors in the transformed measurement, and that can make a big difference to the quality of the estimates, whether they are efficient and so on. So, those are simple approaches. Normally you do not apply such methods in a setting like this where you are learning some advanced stuff as far as nonlinear least squares is concerned. As far as time series analysis is concerned, you are learning the very basic stuff. Fine. So, let us now go ahead with the maximum likelihood and Bayesian estimation. We will go through a quick roundup. I have already explained to you. So, in the last few classes we have learned extensively, at least reasonably extensively on the principles of least squares method, when they give you efficient consistent estimates and so on. We have gone through the ideas of weighted least squares and nonlinear least squares. We have already looked at maximum likelihood estimation principle when we were learning Fisher's information. So, the idea is not new as far as Fisher's MLE is concerned, but let us take a closer look at MLE today, again using our classic example of estimating the mean, and then quickly move on to Bayesian estimation. Again we will study Bayesian estimation in the context of estimating mean. So, that estimation of mean is a beautiful example that helps us illustrate several methods. So, we know I am going to skip the concept of likelihood, and just to refresh, likelihood function is nothing but the PDF, but fundamentally or philosophically they are two different things. The PDF is a function of y and the parameters are fixed, whereas a likelihood function is conditioned on a given data set, it is fixed and the parameters are free to vary. And maximum likelihood principle believes that the winner among the unknown PDFs, candidate PDFs, is the one that produces the observations with the maximum probability, and that happens to be the PDF proportional to the PDF, and that is why you have the likelihood function. So, instead of maximizing the likelihood, we maximize a log likelihood for mathematical tractability, or rather numerical tractability, and therefore, we come up with this kind of an objective function. Although we say maximize log likelihood, typically all optimization problems are presented as minimizing something. So, we say minimize negative log likelihood. Now, there are some packages in R which will do the MLE for you, but I do not see why you need a package for MLE unless you say, well, here is the data and I mention the type of PDF. For example, there is a routine called MLE, I think it is in stats4 package if I am right. All it says is give me the log likelihood function. If I am going to pass on the log likelihood function, why do I need MLE? Well, there is a reason, but still after all, once I construct the log likelihood function, it is only an optimization problem. There is a reason why there is an exclusive routine for MLE, even though you have to manually construct the log likelihood, and I will tell you a bit later, but by and large you do not need an exclusive function as long as you have access to an optimizer, a nonlinear optimizer. If this package or routine somehow helps you overcome this step of constructing the PDF, all you have to say is I have Gaussian, I assume that the data has a Gaussian distribution and so on, then it is okay. But you may not find such specialized packages, at least to the best of my knowledge. It is better for you to manually construct it. What I am going to show you, we will skip the procedure, we know that. I am going to take you straight to the example. What I am going to show you now is how to set up the MLE for the estimation of mean. We have seen that already, almost half, 75% of it we have seen when we were computing Fisher's information. But now we will look at it from an estimation viewpoint rather than a Fisher's information viewpoint and observe close similarities with least squares. Later on, that is tomorrow or a bit day after, when I show you how these methods are applied to estimating time series models, then you will realize that a significant effort from the user side in MLE is in setting up the likelihood function. Once you have set up the likelihood function, then it is the computer Baba's work, not our work. It has to find the optimum. Okay. Our role kind of ends there. So, the procedure for any MLE, at least there are different ways, but this is a very standard procedure that you can adopt for solving any MLE problem or setting up likelihood function. First, given the observations, you have to write a model, that which we have already said, the model maps the parameter space to the known space. So, here I am given observations of a Gaussian white noise process, and I am interested in estimating now the mean and variance. So, the model that we write, as I have written on the screen, is C plus Ek, or you can say mu plus Ek, does not matter. You can think of this as mu y, does not matter. Now, the first step in likelihood method is in setting up the likelihood of these n observations. And remember, since we are going to work with n observations to collectively, we have to set up a joint PDF. That is where the story begins. Here it is a lot easy in this example. When I show you how to set up MLE for AR1, you will feel the flame turned on a bit more. Right now there is no flame per se, it is fairly easy. So, the joint PDF of these n observations has to be written first by identifying the source of randomness in y. So, the source of randomness in y is this Ek. One begins from that point. You say this, you make assumptions on the source of randomness in E. First you identify the source, which is Ek here, and then you have to make assumptions on the PDF that is generating the source, and it is already given to us, it is a Gaussian white. So, Ek is a Gaussian white noise process. Therefore, I know, so now then the next step is asking how does the source uncertainty propagate to the measurements, right. The step 1 is to identify the nature of uncertainty. in source that is generating your measurements, and then determining how the source uncertainty propagates to the measurements. So, here the source uncertainty is Gaussian white, and if you ask how does it propagate to y, it is fairly straightforward. It just propagates and results in a Gaussian y, right. If Ek is Gaussian, Yk is also Gaussian, only mean shifted. So, that makes it easy, but that is a single, as far as a single observation is concerned. Now, I have to consider n observations jointly. When I am looking at n observations jointly, I have to worry about the correlation or the dependence between the observations. In fact, specifically the dependence, because that is what determines the joint PDF. In this case, we are lucky because it is Gaussian white noise. We know that uncorrelated, since Ek is uncorrelated, Yk is also going to be uncorrelated. On the other hand, if you had an AR1, just to give you a glimpse, suppose Y was being generated by an AR1 process. Again step 1, so the goal here would be to estimate the model parameter D1, if necessary the mean of Y, otherwise you say well Y is 0 mean, but definitely D1 and sigma square E. So, in this case again you start with the same question, what is the source of randomness in Y? Ek. What is the nature of such randomness? Gaussian white, let us say you are given that. Now, you have to ask if Ek is Gaussian white, what is going to be the nature of Yk in terms of distribution? That we know because it is a linear process. We know that a Gaussian nature is going to be transmitted to Yk as well. But the difference between Y and E is that Ek's are uncorrelated, whereas Yk's are not. So, that brings in a dependence, and writing the joint PDF is not going to be straightforward. It is going to be not difficult, but it definitely it is not going to be straightforward. So, we will learn a bit later as to how to handle correlated series. Here there is no correlation among Y, so it is fairly straightforward. We have done this before. We say that this is a product. Since you have to be careful here, since you are looking at Gaussian uncorrelated series, you might as well call the series as independent. If it was some other distribution and still being uncorrelated, you cannot claim independence. Remember, only for Gaussian processes uncorrelatedness means independence. So, you have to keep that in mind. That is it. So, you say this is a product, right, that is exactly what it is, and the PDF of a single observation is written on the screen for you. It is your standard generic Gaussian distribution with a mean C and variance sigma square E. How did I write this? In doing this, we had to first determine the PDF of Y. Since I am given Ek is Gaussian, Yk is Gaussian, step 1. Then remember that in order to write the PDF of a single observation, I need to know the mean of Y and variance of Y. So, mean of Y is clear, it is C. I have to be now alert when it comes to calculation of variance of Y, whether it is the same as E or something else. What do you think? The variance of Y, what is it? It is the same as sigma square E. Again, it is a simple one here, it is a no brainer, but here one has to be careful. Assume that this is a stationary process. Assume Ek is 0 mean, we have shown that Yk is 0 mean, but the variance of Y is not the same as variance of E. What is the variance of Y in the AR1 case? By 1 minus d1 square. So, you have to be careful when you write the PDF of a single observation. Here it is straightforward. So, here we know that mu Y is C and sigma square Y is sigma square E. So, using the fact that Yk is Gaussian, it has a mean C and variance sigma square E, we write the Gaussian PDF here. That is it, and then we put together the PDFs as a product, and that is what that is the expression that you get in equation 7, right. And the goal, and now this is my likelihood function, where I am given Yk's and I do not know C and sigma square E. So, the optimization problem is that of maximizing the log likelihood or minimizing, in fact, there should be a minus L here in equation 8, I will correct that at the front, minus big L. So, the optimization problem is that of minimizing the negative log likelihood. So, here you see the negative log likelihood. Now, if you look at this expression 8 carefully, particularly pay attention to the last term, that is something that we have seen before, right. We have seen this before, this expression, that last term which has a summation, we have seen that before in the context of least squares estimation. If you recall, when we set up the when we introduced estimation with this example and we said we would like to minimize the sum square error, which is nothing but the least squares idea, you encounter this term. Naturally, therefore, least squares is embedded in MLE. We did not start with the least squares idea at all. Look at this, Gauss preceded Fisher at least by 100 plus years. He thought of least squares, but when it came to Fisher's turn, by when Gauss had actually already atomized, you see MLE which embeds least squares. On the other hand, if you look at Bayesian, Bayesian precedes MLE, at least the idea of Bayesian, Bayes rules and so on, but we will see shortly that Bayesian ideas include MLE as a natural thing. So, in the order of hierarchy, you see least squares and then MLE as a superset and then Bayesian as even a superset. So, always remember this, that you will naturally be working out on least squares methods the moment you work with MLE, but with a Gaussian distributed errors. You would not run into this expression if I were to tell you that Ek is IID with a Poisson distribution or with a uniform distribution or some other distribution. I tell you that Ek's are independent, but it is a non-Gaussian distribution, let us say. Then you would not run into this kind of expression, which means that least squares is a special case of MLE with Gaussian distribution. That is very well known. I am just telling you, giving you this information, probably that is coming to you as the first time in your life. Now, apart from this summation here, there is another term that has to be optimized. In total, there are 3 terms, but the first term is a constant, so we can ignore that. It is independent of theta. The second term is only dependent on sigma square E, and the third term is dependent on both C and sigma square E. However, you can pull out, you may say it is not exactly identical to least squares, because in least squares I had only sigma yk minus E square, but you can pull out the sigma square E out of the summation and basically see that you are giving, or you can include that and you can say that you are including a weighting of sigma square E, which is the same for all observations. Gradually you should sense, you should now smell that even weighted least squares is perhaps a part of MLE. Okay, it is not just ordinary least squares, even weighted least squares can be shown to be a part of MLE. We will come to that very quickly. So, the point here is least squares is a special case of MLE with Gaussian distributed errors, and that MLE looks at solving a different kind of optimization problem with least squares embedded into it. Now, obviously, in this case, this is so special that you can come up with an analytical solution straight away. What is the estimate of sigma square E in this case? C we have already solved, it is a sample mean. You can see straight away minimization of this with respect to C will get you the sample mean. So, sample mean is also the maximum likelihood estimator. Sigma square E estimate, optimal estimate, turns out to be what I show you here in equation 10. It is our biased estimator of variance. It is not your least squares. If it were to be a least squares estimator of variance, you would see a 1 over n minus 1, right. What do we do in least squares method? We first estimate the unknowns, parameters, unknown here is C, and that turns out to be sample mean, and then you estimate sigma square E as some square error by n minus p. The sum square error is sigma yk minus y bar square divided by n minus p in least squares, where p is the number of parameters you would have estimated, which is 1. That is why we have a 1 over n minus 1. In MLE you have 1 over n, right. So, in MLE, in general MLE will lead to biased estimates. Sample mean is unbiased, but that is just a coincidence. In general you can expect maximum likelihood to give you biased estimates, but we know that is asymptotically unbiased. So, as n grows large, the bias vanishes. So, which is very good. That is why maximum likelihood estimators are good, in the sense, and for as n becomes large, it will give you asymptotically unbiased estimators. But there is a more important property why maximum likelihood estimators are preferred, because it gives you the most efficient estimators. That is point number 1. Point number 2 is it naturally accommodates heteroscedastic errors as well. What I mean by that is, if I were to tell you, go back to this problem and I tell you that Ek is white, in the sense it is uncorrelated, but it is heteroscedastic. That means its variance changes with time. Where would you see the change coming in? In equation 6 you would have sigma square k, right, the variance of the kth observation, and all these equations would be affected. Instead of the same weightage to all observation, you would have observation dependent weighting. That is nothing but your optimal weighted least squares method. Weighted least squares with the optimal weighting already incorporated. When we formulated the weighted least squares, we had to take 2 steps. First, we had to modify the OLS by introducing a weighting matrix, and then ask the question, what kind of weighting matrices would give me efficient estimates. In MLE you do not have to ask such questions at all. Straight away it is taken care of, the weighting is taken care of, the optimal weighting is also incorporated. As a result, you should expect efficient estimates. Of course, you can solve this assuming sigma square k is known. If it is not known, then you have to estimate them iteratively, that is another issue. But what I am trying to tell you here is, the weighted least squares is a special case of MLE with heteroscedastic Gaussian errors, uncorrelated Gaussian errors. So, that is it. So, MLE incorporates least squares, weighted least squares, and if necessary even nonlinear least squares, depending on the predictor that you have naturally. So, some of the just as a quick numerical example I am showing you, just I have randomly simulated about 200 observations of a Gaussian white noise process with mean 1 and variance 2, and I am reporting to you the maximum likelihood estimates. This is nothing but your sample mean with the standard error, and this is the estimate of the standard deviation. Standard deviation is sorry, it should be standard deviation, not variance here. So, the standard deviation turns out to be 1.82, pretty close to the true value with this error, and the 95% confidence intervals are included here. Once you derive the estimator, then you go through the standard questions, whether it is consistent, efficient, what is the distribution, and all of that. We have already discussed what when the sample mean is by unbiased estimator and so on. We have also discussed about the sigma ML as well. Now, of course, in this case you could use least squares as well, but in general MLE is preferred. Okay, so some remarks on this example. We have talked about a few things already. I am going to actually go past these. There is one remark that I want to draw your attention to, which is that the maximum likelihood estimate of sigma E is the same as first estimating sigma square E and then taking a square root. Remember, when we talked of Fisher's information, we said the Fisher's information of theta is different from Fisher's information of g of, that is, if there is a parameter theta and then you are looking at estimating g of theta, then in general the estimation of g of theta is not necessarily, the optimal estimate of g of theta is not necessarily the same as first optimally estimating theta and then taking g, right. If theta star is an estimate of theta and I am looking at estimating g of theta optimally, then g star of theta. So, if you say the star is not necessarily equal to g of theta star in general, but with maximum likelihood it has a beautiful invariance property which says that you do not have to worry. If you want to estimate g of theta, simply obtain ml of theta. If that simplifies life for you, estimate theta first and then take the transformation. That is what this expression is telling you. You do not have to again solve the MLE with sigma e as unknown. You do not have to do that. You can simply estimate sigma square e like we did and then take the square root. This is called the invariance property of MLE. I am giving you certain things without proofs. If you are interested in proofs, certainly you should go and look up a standard textbook on MLE. Okay. And finally, you can show that the asymptotic distributions of all maximum likelihood estimates are Gaussian distributions. In this case, the parameters of interest are C and sigma square E. These are asymptotic distributions, which means large sample cases only. Although I am giving you these distribution results for this example, in general, if you take any maximum likelihood estimate, its asymptotic distribution is going to be Gaussian. Let me ask you a simple question. What is a finite sample distribution of sigma square hat? What is it? If the observations fall from a Gaussian white noise process, then you are right, sigma square E hat will follow chi-square distribution, but that is finite sample distribution. This is large sample distribution, and we know that if you look at a chi-square distribution, in fact the answer is not complete. You should say sigma square hat is a chi-square distribution with n minus 1 degrees of freedom. As n grows, the chi-square distribution tends to look like a Gaussian. So, that is one way of at least verifying this statement that I made in equation 14, because these are asymptotic distributions, these are large sample distributions. Therefore, you should not be surprised that root n sigma square E hat follows a Gaussian distribution, whereas we are bombarded all the time with the chi-square distribution. Okay. So, so much about MLE. I have already talked about the weighted least squares part. Very quickly, I just want to talk about computing MLE. I will not go into any details. I just want to tell you that in general, any MLE will lead to a non-linear optimization problem. There is no doubt about it. However, there are certain specialized algorithms. So, you can use your standard Newton-Raphson method, Gauss-Newton method and so on to solve the non-linear optimization problem. But it turns out that there are some specialized algorithms that are written for MLE because of the nature of the likelihood function and the kind of problems that you expect to see. Some of these, at least 3 of these are called, one is the Fisher scoring method developed by Fisher. It is a variant of Newton-Raphson method. The other is called the polytope method, which uses a gradient search kind of approach. This is also incidentally called a simplex algorithm, but this is not the same simplex that you encounter in LP, in linear programming. And the third is called the EM, or the expectation maximization algorithm, which is very popular, that is used in solving MLE. Again, I will not go into the details, but these are perhaps a reasons why there are routines specialized for MLE, which are asking you to give the to supply the likelihood function, and they use one of these algorithms to get the optimum value for you, right. So, I have given you the references, you can look up the details if you are interested in these algorithms, but just to let you know, and I am going to skip the asymptotic properties. One point that I want to make in passing is the asymptotic efficiency. We have talked about asymptotic normality, asymptotic efficiency, which has got to do with the variance of the estimator. You can show that the maximum likelihood estimator results in the Cramer-Rouse lower bound as n goes to infinity, and that is one of the reasons. Apart from consistency, the asymptotic efficiency is the one that makes ML methods very attractive, maximum likelihood methods very attractive for large samples. For small samples it has poor performance, there is no assurance, but for large samples ML is good. And one point that you want to keep in mind with maximum likelihood estimators is that it is applicable only if your PDF satisfies the so called regularity conditions. We have talked about that when we discussed Fisher's information. One of the conditions that for the PDF to be called as regular is the range of the parameters value should not determine the range of possibilities, range of outcomes, and a classic example is the uniform distribution. So, you should make sure that your PDF is regular. By and large, you will see in the literature ML problems being set up for Gaussian or a few non-Gaussian. If nothing is known, always maximum likelihood problems are solved for Gaussian because it is easy to solve, that is all. It does not mean that it is a truth. Okay? And we have talked about invariance, and that kind of brings us close to the MLE. So, ML estimators large sample properties are very attractive. It is consistent, efficient, it gives you Gaussian distribution, it has invariance property, very good. But remember that ML methods are not so great for finite samples, remember that.